In this video, I'll talk about the chi-squared goodness of fit test, and I'm going to go through two examples. The first will do an example where we're looking at a multinomial probability distribution, and the second example will look at a normal distribution. So for the first example, we're going to consider three companies, A, B, and C, that make a particular product, and company C is trying to see if a new product that it's bringing out will increase the historical market share that the companies typically have. These market shares are represented here by hypothesized proportions. So historically, company A has a 30% market share, company B has a 50% market share, and company C has a 20% market share. The marketing research firm has asked a panel of 200 customers which of the three products they prefer, and these are the results. So 48 preferred the product from company A, 98 preferred the product from company B, and 54 preferred the new product from company C. So we can assess whether there's a change in the market share by doing a chi-squared test to compare the observed frequencies or the observed proportions with the hypothesized proportions, the historical market share. So the observed frequencies we can present in a table, and then the expected frequencies are going to be calculated using the hypothesized proportions multiplied by the sample size. So that's what these numbers are here. And then the chi-squared test statistic will be calculated in the usual way by taking the observed number minus the expected number squared divided by the expected number. And we'll do that for each of the values in the table. So all three values, and then we'll sum them to get the chi-squared test statistic, so 7.340, and then we'll look at a chi-squared distribution with count the number of probabilities that we're looking at, the number of categories, and there's 3 in this case, and then subtract 1 from that to get 2. So we've got 2 degrees of freedom for our chi-squared distribution. And the right tail area to the right of 7.34 for a chi-squared distribution with 2 degrees of freedom is 0.0255. Compare that to our significance level. And because 0.0255, our p-value is less than an alpha of 0.05, we reject the null hypothesis. So we can conclude that indeed there is a shift in the market share based on this consumer panel. We could use a critical value to do the test instead. So that would be, again, using the chi-squared distribution with 2 degrees of freedom. And with a 5% tail area, the critical value is 5.991. And the chi-squared test statistic, we see if it's in the rejection region to the right of this critical value, and it is. So same conclusion, we reject the null hypothesis. So let's use Excel stat to do that analysis. So this is parametric tests and multinomial goodness of fit. And we select our frequencies in our sample. We select our expected proportions. So these are the historical market shares for this example. The data format is in proportions for the expected proportions. We have column labels, and we're doing a chi-squared test. So here are the results. And 7.34 is our chi-squared test statistic, 5.991 is the critical value, 2 degrees of freedom for the chi-squared distribution, and a p-value of 0.0255. And that matches what we got here. We could present the analysis here using a bar chart, we could look at the expected proportions and then compare them with the observed proportions. So these observed proportions are just taken from the observed frequencies, dividing by the sample size. And if I insert a chart here, a bar chart, we'll get a visual representation of the results. And here we can see the expected proportions in blue, observed proportions in orange. And it looks like this is company C, the new product. So they're increasing their market share from the historical norm. And it looks like it's at the expense of company A, because their market share has gone down, whereas company B's gone down a little bit, but not by as much as company A. So let's move to the second example now. So this is an example of, we have some data here on some test scores, and we want to see if those fit a normal distribution. So what we do is we imagine a normal curve, and in this case, we've got a sample size of 50, and for the chi-square distribution test to work, we need at least 5 observations, 5 expected observations in each cell. So if we divided 50 into 10 intervals, we would have 5 in each cell. And the way that we can do that is look at the 10%, 20%, 30%, and so on percentiles of a normal distribution. So that's what these numbers are here. So they're just calculated using norm.inv. And then if I convert those percentiles into values that match up with the sample data, so I do that by multiplying this number by the sample standard deviation. So that's this number here. And then adding, I multiply this number, the Z number, by the standard deviation, and then I add the sample mean. So that's what this formula is doing. Sample mean plus the Z number times the standard deviation. So I do that for all my Zs. So I'm converting my Zs essentially to numbers that match up with my sample. And then I can create intervals using these values. So the first interval will be everything up to 55.07. The next interval will be everything between 55.07 and 59.66, and so on, all the way up to the final interval is everything bigger than 81.77. And because of the way we constructed this using normal Z numbers, percentiles from a normal distribution, the expected number in each interval is 5. Whereas the observed frequencies, well, that's going to depend on the data. So I can use Excel, use the COUNTIF function to see how many are in each interval. So this is telling me there's 5 in the first interval, 5 in the second, 7 in this one, 8 in this one, and so on. And then because I've got observed and expected, I can calculate the chi-squared test statistic using the usual formula, observed minus expected squared divided by expected. If I add all those up, I get 6.4. So that's my chi-squared statistic. I can calculate a p-value. The degrees of freedom here is the number of intervals minus the number of parameters we use to estimate the normal distribution. And we use 2 here. We use the mean and the standard deviation. So that's what this 2 is, the formula, and then minus 1 as usual. So the degrees of freedom here is 10 minus 2 minus 1, which comes to 7. The p-value for the chi-squared distribution with 7 degrees of freedom, the tail area to the right of 6.4 is 0.4939. It's pretty big. So even at an alpha of 0.1, we're not going to be able to reject the null hypothesis here. The null hypothesis says this distribution is normal. It's a normal distribution. So we're not rejecting that. So we're concluding that this data could well be from a normal distribution. And you can get a sense for that from these observed numbers here. They're all pretty close to 5. So we're very close to being a normal distribution here. Alternatively, you could use a critical value here, and you would look at whether your test statistic is above that critical value, which it isn't. So again, we fail to reject the null. Let's see if we can get Excel stat to do this. So this particular test is under, let's see, where is it? I think it's actually under modeling data and distribution fitting. So if we select that, and then we select our data, so I've selected our data, we'll test against the normal distribution. There's a whole bunch of distributions you can test against, but we're just going to do the normal distribution. We're going to estimate the parameters from the data, and under options, we're going to use a chi-squared test. We use a significance level of 5%. And there's different ways that the intervals could be calculated. And the default is just to pick 10 intervals. So that's what I'll do here. It's actually not going to match up exactly with what we did by hand, because the way it determines the intervals is a little bit different. And then the estimation method, both of these are going to give similar results in this case, so we'll just leave it at the default. Okay, and let's see what the output is on the charts. Okay, all right. So let's see what happens. So as I say, the results are going to be a little bit different, but they'll be pretty close to what we did, because it's very similar. So this is telling us, so here's the sample mean and standard deviation. So that's what we calculated. Here's the details of the chi-squared test. So they got a chi-squared test statistic of 6.395. It's actually very close to what we got. And the p-value 0.494, again, very close to what we got. So as the computed p-value is greater than the significance level, we cannot reject the null hypothesis. And the null hypothesis is that the sample follows a normal distribution. And then here's the table it came up with. So the intervals are a little bit different. And what it does is, so these are the observed counts within each interval, but it doesn't have 5s all the way down here. So this is where it differs from what we did. These are the frequencies for the assumed normal distribution, and they're a little bit different to what we calculated. But it looks like the end result was pretty much the same, that the chi-squared values added up to 6.4. And then here's a bar graph showing you the observed frequencies in green, and then just the white bars with a red outline there. Those are from the normal distribution, and you can see it's pretty close. Okay, so that's the chi-squared test used as a goodness of fit test in 2 different contexts, for a multinomial and for a normal.